Okay.
It makes sense.
So tonight,
Sorry.
this evening, I was just going to over a bunch of practice problems that I came up with this afternoon. And encourage you to interrupt me. You know, if I'm doing something that you don't understand, that's not okay. Stop me and we'll help you understand. So also, if you find that what I'm doing is just, you know, way too basic, then, you know, suggest something else. I'm going to start with a very basic problem. And I think that the video is recording from that blue line to that blue line. So I'll just start over here. If I have a rock that has a mass 400 grams, a volume of 100 cc's, and I hold this water, this looks like one of your homework problems, and I let it go. What kind of acceleration does it have? And because this is water, really easy to work with. First of all, we have to find the buoyant force. And to find the buoyant force, we imagine a ball of water that's the same size and shape as my rock. And so it will have 100 cc's volume. Now, what I want is the weight of that ball of water. And in order to find the weight of that ball of water, I got to know how many kilograms of water I've got there. Well, it's easier to find out how many grams there are, because for water, there's 1 gram for each cubic centimeter. Okay, and so that means if I've got 100 cubic centimeters, I've got 100 grams. And if I move my decimal place 3 places over, that's going to be 0.1 kilograms. Everyone with me so far? Now, what that means is that the buoyant force, well, first of all, the weight of this water, of the ball of water, is going to equal 0.1 kilograms times 10, or 1 Newton. And because that ball of water is not going anywhere, that means the buoyant force on that ball of water must also be 1 Newton. And because this has the same shape and volume as my rock, that means my buoyant force on the rock is also 1 Newton. So the weight of this rock is 4 newtons. Does everyone see how I got 4 newtons from that? Okay, this is just 0.4 kilograms. Again, I just moved the decimal place 3 places over. So now, if I use Newton's second law, well, I have 4 newtons down, I have 1 Newton up. That's a net or unbalanced force of 3 newtons down. So this is going to be 3 newtons down. The mass is 0.4 kilograms. And so that means my acceleration is going to be 3 newtons divided by 0.4 kilograms down. And that's going to be 7.5 meters per second squared down. It's going to sink like a rock because, well, it's in the rock. Okay, fair enough. Hey, welcome. That's the most basic that we got. So let's start there. How questions about that?
Questions are.
Wait, how did you find the buoyant force again on that?
Oh, you imagine a a ball of water exactly the same size as your rock. And then you put that ball of water on a scale that registers in newtons. And that's your buoyant force.
So whatever like the displaced
So
liquid
if
is.
this took up 100 cc's of volume, 100 cc's of water, because water's got this really cool density of 1 gram per each, that's gonna be 100 grams of water, which is 0.1 kilograms of water. And then I multiply that by G.
You're able to do that because the rock was submerged, so it's the volume.
Yeah. If something's submerged, if anything's submerged, what you're looking for, what you're dealing with is the volume of the object. Because where it is now, water used to be. Okay. So let's spice this up a little bit. What if instead of water, this was heavy cream? With a density of 1.5 grams per centimeter cubed. We got the same rock, the same mass, same volume. And we still want to find the acceleration down. Well, first of all, will it sink? Well, the density of this rock is the mass divided by the volume. That's going to be 4 grams per cc. So that's bigger than heavy cream, so it's going to sink in the heavy cream. But what acceleration? Well, if I draw a free body diagram, the weight force, Earth on the rock, is still going to be 4 newtons. The Earth doesn't care whether this rock is in water or heavy cream, it holds the same. Okay, just the mass times G. But the buoyant force is going to be bigger. Okay, well, how much bigger? Well, with water, 100 cc's had a mass of 100 grams. But heavy cream says, I've got 1.5 grams for every cc. And if I've got 100 cc's and I got 1.5 grams for each, that means that I'm going to have a ball of cream. That ball of cream is going to have a volume of 100 cc's, but a mass of 150 grams. Does everyone see where I got that? Okay, from our density. If you're a math person that has to see the math, density is equal to mass over volume. This is 1.5 grams per cc. I'm looking for M, and I have 100 cc's. I just solve for M, and I get 150. Now 150 grams is 0.15 kilograms. And so that means the buoyant force here is not going to be 1 newton, but the buoyant force will be 1.5 newtons.
Can you show the math for that? Sorry.
Should I show the math for that?
Can you show the math for it? For the buoyant force?
The buoyant force is the weight of the liquid that got displaced. Since I displaced 150 grams of heavy cream, or 0.15 kilograms of heavy cream, the weight force of this would just be the mass, 0.15 kilograms, times G, which is 10 newtons for each kilogram. And that's going to be 1.5 newtons. It's just like what we did in the second part of the class, as we prepared for that second exam. Whenever we wanted to weight, we just took whatever the mass was in kilograms, multiplied by 10.
I understand that. What is confusing me is, so if it's submerged, we're supposed to be using the volume. So why did we use the mass this time?
Oh, by Archimedes' principle, it's always the weight of the fluid, never any different than the weight of the fluid displaced. But if something's submerged, I get the weight by looking at the volume of the object and then using the density to figure out m, and hence how many kilograms are displaced.
Okay.
Okay, when something is floating, then the whole volume of the object is not displacing liquid. And so then I don't look at the volume of that object is no longer relevant. Okay,
So basically, when we're doing these problems, when it's submerged in water, we only just use the volume because it's multiplied by one.
I'm sorry, say that again.
So when we're doing these kind of problems in water, the volume, we just kind of use the volume, so it's just multiplied by one. And
Well, in anything that's submerged, you start with the volume of the object. And then you find from that the mass of the object with the density equation. With water, it's really easy because it's 1 for 1. With heavy cream, it's not so easy. It's 1.5 for 1. And so ultimately, in both cases, I was looking for the mass of liquid displaced. It was just easier with water. Okay. Now, if we wanted the acceleration of this rock in heavy cream, you expect it to be bigger or smaller than in water? Smaller. And that's because its buoyant force is bigger. I've got 4 down, I've got 1.5 up. That means instead of 3 newtons down, I just have 2.5 newtons down for my net force. The mass stays the same, that's 0.4 kilograms. And now I'm gonna get something that's smaller than 7.5 billion.
I'm just confused with the formula going towards the density times volume times the gravitational pull. Like, where does that come in?
Oh, well, if you want to use that formula, you can fail the next exam. That formula is just worthless. Every time you use that formula, it gives you an answer that's 1,000 times too big.
Like,
So why did I put it in the back of the chapter? I didn't. My co-author did. I fought him on it. I said, if you put it back there, people are going to use it. Don't put it there. Now, I use that formula, but in 2 steps. The formula for the buoyant force, according to the book, is rho g volume, right? Well, what I did was I took those two, right? If I'm looking for the mass, let me solve this for the mass. The mass is just going to be rho times the volume, right? That's how I got the 150 grams. The problem is, if I put that in for rho and B, I've got grams. And G is in kilograms or newtons for each kilogram. And so I've got to convert from grams to kilograms before I can use that formula. So I like to do it in 2 steps. I first of all find the number of grams with the rho times V part of that equation. And then I convert it from grams to kilograms. And then I multiply it by the G. Okay. It's like a 2-step dance. Okay. You gotta do the first step before you do the second. Now, questions? We're good? Okay, let's move on to something that floats. What if I go back here to this ball? And I look in water. But this time I'm gonna turn things around so that the mass is 100 grams and the volume is 400 cc. Now, if I look at the density of that ball, I have mass over volume. That's going to be 0.25 grams per cc. That's a very, very light oil, super light. And or some, I misspoke. It's not a liquid, it's a ball. And it's made out of some sort of plastic or styrofoam. Very small density. Okay, so you know that it's gonna take off towards the surface and it's gonna float. Well, how big is the buoyant force on that? Well, let's do the steps. Because this is water and because it's submerged, completely submerged, I look at the volume and I say, I'm displacing that many cc's of water. That means I'm displacing 400 grams of water because it's 1 for 1. And that is equal, here's where I do the conversion, 0.4 kilograms. And that ball of water is going to weigh 4 newtons. And that means that the buoyant force on this is going to be 4 newtons. Well, the weight, I mean, this is 100 grams, which is 0.1 kilograms. That weighs 1 newton. And so this is just the opposite of what we saw before. Now I've got a net force of, so by F net equals MA, I have 3 newtons up before I had 3 newtons down. But now the mass is only 0.1 kilogram. And that means my acceleration is going to be 30 meters per second squared up. This thing is just going to go popping up toward the surface. And then when it gets to the surface, it's going to float. And it's going to float such that it displaces an amount of water equal to its own weight. When something floats, it tells you about the weight of the object. Always remember that example from class. A 10-ton ship has to displace 10 tons of fluid in order to float. Now, that means that it's going to displace 100 grams of water. Well, 100 grams of water is 100 cc's. If the whole ball has 400 cc's, that means I've got 300 cc's above the surface of the water and 100 cc below the surface of the water. What that means is you can only see 3/4 of this ball, which means you can't see 1/4 of the ball. And that tells me that the density of the ball must be 1/4 of the density of water, or 0.25. And that's what we knew. Okay. Jenna?
So you said that when an object floats,
what it displaces is its mass? Is that what?
When it floats, it has a buoyant force equal to its weight.
Okay, and then,
How do I know that? Because when something floats like this,
Massive water, or a massive liquid.
there's only two forces on the free body diagram. There's the weight down of the object and the buoyant force up. And if it floats, it has zero acceleration. So those have to balance each other. So what was your question, Jenna?
okay, wait, my question was that it's displacing the mass of the water or the object? Because how'd you get the 100 cc?
Well, if I look at these two forces, this weight force is the mass of the object times G, and this is equal to the mass of the liquid displaced times G. So if they're equal to each other, the G's will cancel, and that means a 400-gram object, grams of liquid, if it's floating.
In this example on the left, where's the 400 grams ball coming from? Like, and also, where did you get the buoyant force for the one that's 100 grams? On the far left?
On the far left,
Yeah. Is the 400 grams just a different example?
the buoyant force is the weight of water that's displaced by the ball. The ball had a volume of 400 cc's, 400 cubic centimeters. So if I imagine a ball of water that
Oh,
the same size, it would have a volume of 400 cc's, but because the density of water is 1 gram for each cc, that's 400 grams. And that's why this buoyant force is bigger than the weight, is because this ball only weighs 1 Newton, but the ball of water it displaced or pushed out of space was 4 Newtons.
okay, thank you.
You're welcome.
The ball's floating.
Floating. Oh, in Heavy Creek. Ah, yes, excellent. That's where we were going next. So if we go into Heavy Creek and we so we have the density of the heavy cream equal to 1.5 grams per cc. And if we take that same ball that has a mass of 100 grams and a volume of 400 cc, well, I imagine a ball of cream that is the same size as my real ball. So it would have a volume that is 400 cc's. Then I would come to this equation here and rewrite it by multiplying both sides by the volume. And I would say the mass of that ball is equal to the density of 1.5 grams for each centimeter cubed times 400 centimeters cubed. That's going to give me 600 grams. And here's the step that's important. I convert that to kilograms before I multiply by G. So the mass of this ball of cream is going to be 0.6 kilograms. And that means this ball of cream weighs, multiply that by 10. And that means that the buoyant force on this ball, when it's in heavy cream, is 6 newtons. Well, the weight force, this is still only 0.1 kilograms. So the weight force here is only 1 Newton. And so now I've got a net force of 5 newtons up, and it's going to really rocket up. Indeed, it's going to go at a rate of 50 meters per second squared, or 5G. If this were you, you'd pass out with that an acceleration. Okay. So, let's look at this ball when it reaches the top. When it reaches the top, I know that the weight force is only 1 Newton. Because it's only got 2 forces on it and it has 0 acceleration, that means that the buoyant force must be 1 Newton. So that means what we're displacing here is 0.1 kilograms or 100 grams of heavy cream. How many cc's is that? Well, now we got to go back to this equation and use it backwards. If I want the volume instead of the mass, I've got to cross multiply this, and that's going to give me the volume is going to equal the mass divided by the density. So I want 100 grams of heavy cream displaced. Heavy cream has a density of 1.5 grams for each cc, and that's going to tell me how many. Oh, I know you don't have to believe this, but there was a time not that long ago when I could do that in my head. Okay, 66.7. So that's going to be 66.7 centimeters cubed. So that means I have 0.7 centimeters cubed.
Oh.
And since the whole ball had a volume of 400, this must be 333 centimeters.
Dr. Francis,
Yes.
so how did you know how much is submerged? Like when it's floating? Like how did you get the 100 grams?
Oh. Because when something's floating, there's only 2 forces on it. The weight and the buoyant force. And because this diagram has to scream 0, they have to be equal to each other. And so that means the weight force, this is the weight of 100 grams. So this must also be the weight of 100 grams.
Okay.
So that goes back to the 10-ton ship has to displace 10 tons of liquid to float.
Okay. Yeah, so the weight force on like how much the object weighs, is that always gonna be equal to how much it is when it floats? Does that make sense? Right, how much it weighs is equal to the amount of.
If you are looking, you remember in the homework, you had objects that you put into buckets that were filled up to the brim.
Yeah.
If you're looking for how much something weighs or how many grams there are, you put it into a bucket where it floats. And then you look at what gets displaced or spilled out. And whatever spilled out, however many grams that is, that's how many grams your object has. But if it sinks, then it tells you about the volume of the object. Does that answer your question?
Yes, thank you.
Was there a hand over here? Yes.
So with the water, the densities were proportional to how much was above and below. It doesn't seem like that's entirely the creek.
Ah, but it is, yes. The density of this, the density of the ball is equal to 0.25 grams per cc.
It's weight.
And the density of the heavy cream is 1.5. And we're gonna find that 0.25 is to 1.5
That's
as
going down.
66.7 is to 400.
Oh, okay, yes, that makes sense.
So essentially, the part that is submerged is going to tell you what fraction is submerged is the fraction of the density of the liquid. Now, there's a whole class of problems that involve tension. And are we ready to move on to those, or are we still have questions about these? Okay. So let's start with water and then we'll move to heavy cream. And if you know how to do it in heavy cream, you can do it in any other liquid. Same process, you just change in your equations. So I'm just gonna use heavy cream as our non-water example. But let's start in water. And let's start with a block blue looks like water. Let's make the block this color. And let's say that it has a volume of 900 cc's and a mass of 300 grams. That means the density of the block is going to be 300 grams divided by 900 cc's, or 0.33 grams per cc. So that's going to float. But I'm not going to let it float because I'm going to tie it to the bottom of the pool. And so the question is, what's the tension and the strain? Now, one of the big takeaways that you should have brought with you in your toolbox from the second part of the course is that anytime you're looking for a force, you start with a free body diagram. So here I have a weight force, earth on the block. I have a buoyant force. And I have this tension force, spring on the block. Now, the weight force I can get from this mass, I just rewrite this as 0.3 kilogram and then multiply that by G, or 10, and that gives me 3 newtons. In water, I imagine a block of water that has exactly the same volume as this block of whatever it is. namely 900 cc's. Well, if I'm dealing with water, the density again is 1 gram for each cc. And so that's going to be 900 grams, which is 0.9 kilograms. And the weight of that, if I multiply by G, is going to be 9 newtons. Well, this block isn't going anywhere. It has 0 acceleration. And so this diagram has to be balanced. And so that means the tension force has to be 6 newtons. Okay. Now, the next part of this kind of problem is you cut the string and you ask the question, what is the acceleration of that block right after I cut the string? Well, by cutting the string, I get rid of this force here. So now my free body diagram just has a buoyant force of 9 newtons, a weight force of 3 newtons, and that means I've got an F net of 6 newtons up. Well, let's use F net equals MA. I have 6 newtons up, and the mass of that is going to be 0.9 kilograms. No, I'm sorry, 0.3 kilograms. And because that's the block. And that means that my acceleration is going to be 20 meters per second squared up. Everyone see where I got that? Okay. Then it gets to the top. And once it gets to the top, its acceleration is 0. Well, the weight force doesn't change. The Earth doesn't care what the block's doing, whether it's at the bottom or the top of the pond. And so my weight force is still going to be newtons. And that means that my buoyant force now is 3 newtons. Well, the volume of the block was 900 cc's, but if the buoyant force is only 3 newtons, that means I've only got 300 cc's of water that are under the surface. That's 600 cc's that are above the surface. Okay. Now, that makes sense because we said the density of this block was 1/3 of the density of water. And so when it floats so that only 1/3 of its volume is submerged. Questions before we do that with heavy cream? Yes.
From the buoyancy force to how much is in the water, how did you get there? You took 3 newtons and you knew it was 300.
Right.
Sorry.
Really limited on range here, sorry.
You took the buoyancy force of 3 newtons and then you knew that it was 300 cubic centimeters.
Did I go so quickly?
Yeah.
Okay, I can only do it quickly in water, because in water, it's 1 for 1. What I do is that this is the mass of water submerged or displaced times G. Well, G is 10, so that means that the mass of the water displaced has to be 3 divided by 10, or 0.3 kilograms, which is 300 grams. And I asked myself, how much space does grams take up? when I'm dealing with water. Because it's 1-for-1.
Okay, or you can look at the density of the,
I could do it also this way and just say, hey, I found the density of the block was 1/3 that of water. So 1/3 of this volume is gonna be submerged.
okay, thank
Either
you.
way works,
You.
okay? Are we ready to do heavy cream? Okay. Let's start over here. So heavy cream is red, and so we've got the same block. It's again got a volume equal to 900 cc's, a mass equal to 300 grams. And that gives me a density just like before of 0.33 grams per cc. The heavy cream again has a density of 1.5 grams per cc. So now if I do my 3-body diagram, my weight force is still 3 newtons. Again, the earth doesn't care whether it's in water or heavy cream, it pulls the same. But my buoyant force now is the weight of 900 cc's. Because it's completely submerged, again, it's tied to the base of to the bottom of the pool. Because it's completely submerged, it's displacing its whole volume of heavy cream. And so I have to know how many grams is that going to be. So I go back to this density equation, solve it for mass. And my mass is going to be equal to the density of 1.5 grams per cc times 900 cc's. The cc's cancel grams, and so that's going to be 1350 grams. Well, that's equal to 1.35 kilograms. I moved the decimal place 1, 2, 3 places. Well, how much is 1.35 kilograms going to weigh? Well, just multiply by 10, 13.5 newtons. So now the tension in that string on the block has to be 10.5 newtons. And that's what you expect. Heavy cream is going to give you a much bigger buoyant force than water because it's more dense. Okay, you're displacing the same number of cc's. Heavy cream weighs more, so that gives you the bigger buoyant force. So now, if I cut this string, now my buoyant force isn't 9 anymore. It's 13.5 newtons. And that gives me, if I do F net equals MA, this is going to be 13.5 up, 3 down. That's going to be 10.5 newtons up. And that's going to equal a mass of 0.3 kilograms times the acceleration. And I can solve for the acceleration. And this time I get 30 and change, 30 something. Okay. Now, when it goes up, now it's going to float. Again, this is heavy cream, which is red. It's going to float higher in the heavy cream than it did in the water. And it's going to float again such that I have 300 grams of heavy cream under the surface. Because it weighs, it has a mass of 300 grams. And when it floats, it displaces an amount of liquid equal to its mass, to its weight rather. Okay, so now I use this formula this way. Say the volume displaced is going to be the mass of 300 grams divided by the 1.5 grams per cc. And that's going to be 200 cc's. And so now what I have is going to be 200 cc's below, and I'm going to have 700 above. How are we doing? Okay. Yes.
Let's just think, does it float up faster and
Yes, because the rate of acceleration depends on how much net force I have. And the weight force doesn't depend on whether I'm in water or heavy cream, but this one gets bigger. But a bigger net force in the denser material.
So originally with the 300, that was what it was displacing in water, but
Yeah.
then it's 200.
When it was in water, in both cases, we had to displace 300 grams of liquid. With water, it's 1-for-1, so it was 300 cc's. With heavy cream, it's 1.5-for-1, so it's only 200 cc's.
Oh,
Now, I'm going to remind you of something I said on the very first day that we started this new material. And that was, we've all dealt with sinking and floating in the 4th grade, again in the 6th grade, and then in the 8th grade, high school science. It feels like it should be trivial. And yet every year I've taught this, and that's been a lot of years, it's always the hardest problem for students. It's the one that students have the lowest score on. So let's give it the respect it deserves and, you know, spend time figuring it out. Yes, Ruth.
Will you go over again? Density ratios and how that applies to the volume.
Oh.
The density of the object over the density of the liquid, or is it the other way around?
So the density of the object that's floating is equal to the percent of the object submerged of the liquid floating in. So if you can only see 60% of the object, that means you can't see 40% of it. And that would mean that the density of the object is going to be 40% of the density of the liquid. Let's say it's water. Well, 40% of is the same as saying 0.4 times the density of water of 1 gram per cc. So that would be 0.4 grams per cc. If it were in heavy cream and you could only see 40%, or you only saw 60%, you couldn't see 40% of it, then it would be 0.4 times 1.5 would be point. Grams.
And that's for 40% is submerged or
Submerged, yeah. Yeah, if you can see 10% of the ice, you can't see 90% of it.
and not.
That's the part that you put in the part submerged is what goes in that formula. The density of the ice is 90% the density of salt water. Fine, we're doing okay. The trickiest problem that you've had so far was the problem where you had two blocks that were connected by a string. And you were told that both blocks had a mass of 500 grams. But that let's change it up a little bit because you saw that problem. Let's make it 800 grams. And this one, block B, has a volume of 300 cc. And we're in water. And we're told that block A, let's say that it floats with 3/4 of the block submerged. And so we want to know the tension in the string. And we want to know the volume of A. So this is going to require free body diagrams. If I start with the free body diagram of block B, I have a weight force of 8 newtons. I have a buoyant force of 3 newtons. And that means I have a tension force of 5 newtons. Draw this a little bit longer. Does everyone see where I got those numbers? For the weight, I just took 0.8 kilograms and multiplied by 10. Here, I thought of a block of water that had 300 cc's of volume. That would be 300 grams. That would be 0.3 kilograms. That would weigh 3 newtons. This diagram has to scream balance. If I've got 8 newtons down, I've got to have 8 newtons up. So now I go and I draw a free body diagram for A. Again, I have a weight force equal to 8 newtons. But now the string is pulling down. The other end of the string is going to pull the same as this end. So that tension of string on A is going to be 5 newtons. And that means I have a buoyant force of 13 newtons. That means that this block, in order to have a buoyant force, has to have it has to displace 13 newtons worth of water. In other words, it has to displace 1300 cc's. Now you'll say, well, Greg, the mass of A is 800 grams, but to float, it's displacing 1,300 grams of water. I thought you said when something floated, it displaced the amount of water equal to its own weight. Well, this isn't free floating. Okay, something's floating when there's only two forces on it, weight down, buoyancy up. And I've got that tension force in there that's changing everything. Okay, so because that block B is pulling A down, it's riding lower in the water than it would if it just was all by its onesies. Okay. Now, if the submerged part is 1,300 cc's and if the volume submerged is 3/4 the volume of A, then the volume of A is going to be 4/3 times the volume submerged. That's going to be 4/3 times 1,300 cc's. And I forget what that is.
1,730.
There's going to be that's going to be 1,733 cc's. Yeah.
Wait, how did you get the 1,300
How did I get 1,300 from this buoyant force? Well,
Yeah.
1,300 is, I got that because 13 newtons is 1.3 kilograms times G, which is 10 newtons for each kilogram. So in order for this to float, my block had to displace 1.3 kilograms of water. Well, 1.3 kilograms, 1.3 kilograms. Now move the decimal place 3 places over. That's 1,300 grams. And how many cc's is that to be? Well, it's water, 1 for 1, 1,300 cc's.
I had a question. So initially, before I started solving the way you did with figuring out the tension, I initially thought, oh well, if it floats with 3/4 of the block submerged, then its density would be 3/4 out of water. But we can't solve it that way because it has that tension.
Yes, that's only going to be true if it's free floating with nothing, without an anchor attached underneath.
Okay, cool. Thank you.
Okay, so I'm following everything you're saying, except for why is the volume all of a sudden 4/3 of it?
Oh, given in the problem, we were told that this A is floating there with 3/4 of its volume submerged. And so if I want to solve this for volume of A, I multiply it by 4/3, that cancels that, that cancels that, that cancels that, that cancels that. And if I do something to the right-hand side, I've got to do it to the left-hand side. Okay. There's a danger, folks. That is, if we keep at this too long, we're gonna fry ourselves. And then we're just gonna get frustrated. And then we're gonna be worse off than we started. So stop and rest ourselves. Again, I'm available if you're still struggling with these ideas, come to my office and we'll work through the idea. We got clear until Friday after Thursday midnight. After Thanksgiving, before that exam. starts. So there's plenty of time to get ready. Don't keep-
Not for the opportunity to do nothing. Only when they. Not only to.
Thank you, Greg.
Those- If you look at the sample exams that I posted at the class note, you'll see that there really aren't very many questions.
Keep it down.
The ones that are there are very
I'm in
basic,
shape right now.
qualitative.
Like,
So it's not nearly the level of what we're doing.
literally same. I just once heard his name, I was like. Yeah, it's like,
The stairs, man, take me out.
Um,
you fucking exact, because I worried about that. I'm gonna open it too. My head
And each of those sample exams have really good
bad. So much better.
questions.
About like.
Right there, and then
We told. I thought they were, but
um,
I think I'm gonna start having. It opens.
something floating with only two pieces on it.
Because
Change.
Yeah, and it's just like, I'm like, are we then like, oh. yeah.
Third floor,
I can just say.
by tying it to something underneath,
And I can do the homework.
that no longer works.
The code change, so the answer code change.
Still 300 grams.
For
but because we're displacing heavy cream, 300 grams only takes up 200 cc's. Volume, but
Yeah.
said
Yeah.
grams.
I go along right now.
See ya. Ethan, right?
Yeah.
Oh, man, I'm on a roll.
You're on.
Bye, Steven. Because the density of heavy cream is 1.5.
So it was 345.
Yes, and if it
Just
floats
the
freely,
Zero.
it's gotta have submerged number of grams as block itself.
Yes, I don't know.
Has to displace 10 tons of liquid.
And then the last one.
Finishing off the recordings here.
Thank you, guys. Thank you.
See ya.
Check it again, because it might have changed.
But it won't change.